because she had to cover something else. And I was just like, oh, jeez. I mean, oh,
How was your trip?
Oh, jeez. My trip was, it was pretty good. I got tricked.
Okay.
Well, I was told it was a fishing trip, and like, I did go fishing, but I also ended up working. Like, tore off the deck, the second story deck, and hanging out on.
Was it somebody's house?
Yeah.
That's so funny. Did they really not tell you? Like,
well, they may have alluded to it, but you know.
Like joke, oh, we're probably gonna upgrade the house a little bit while we're down there. No, really. Oh, we won Family Feud. My group did at prom or after prom.
Yeah, I heard your name on the announcements.
That wasn't that. That was different. What was your name on the announcements for? I won a grand prize too. What was it? Dog. What? I got the season tickets to all the plays and musicals. At Fairmont? Yeah. Why would you put your stuff in that? I don't know. I put all of it.
So let me set this up for you. I decided on you gotta set the table.
You said why? Why? Oh, I got like 5 t-shirts. Was my name on the announcements? It wasn't. Oh, darn. I think I put mine in the picnic basket. What? I put mine in the picnic basket. Oh, yeah. That would be so fun on. I don't know. I was trying to go for one that people wouldn't really put in it. Like, you mean like the musicals? Yeah. I didn't even see that one. Although, I mean, I get 2 free tickets to the musicals. Yeah. Is that Friday? Friday and then 2 on Saturday. And maybe 1 on Sunday. Can I take my mask off? Me too. My ears hurt so bad. I've never had problems breathing with the mask until like a couple days ago. Every time I wear a mask now, it's just like really difficult.
I'm so sick of this.
You can take yours off. Are you filming this for them?
Huh?
Are you
Yeah.
filming this for them?
That's why I certainly am not taking off my mask. Look how different you look. Like I haven't seen you without a mask on. Like, you look so normal.
He's just staring at me.
Look at you. Watch seeing you without a mask on could swim.
Yeah.
Saw that a lot.
I used to eat in here sometimes.
Okay, so C is going to be a closed path in space. Okay, so like just like that. And S is going to be any surface that's bounded by C. So what do I mean by that? Is one, like S could be just the surface that's enclosed by the path. That's one possibility. S could be a surface like this. Like, you know, where, you know, there's the surface and I've got, you know, that roof on it, you know. Could be anything, all right? This right here oh, and let F be a vector field.
I don't have room for that.
What? You don't remember vector fields?
I don't have room for that on my paper. I already drew under my sentence. It's not writing it.
Okay. What?
That's like everything we've done smushed together. I can never draw those intervals with a circle on it. My circle's always lost it. What I do.
So what is this saying? Do you remember this quantity when we did Green's theorem? Do you remember what we called that?
No. Oh yeah.
And what did we say was the curl of F was? The circulation density. Remember that?
No.
Well, okay. If C is a closed path, this right here is the circulation of the F along the path. Right? Remember this?
Yeah.
The right side? If C is closed, F dot dr we said was circulation. Remember, we're really talking about flux, circulation, circulation, flux, flux, circulation. F dot dr is the circulation. Okay? Well, one way of calculating F dot dr is by doing this surface integral. This surface integral that's actually equal to a flux integral. Okay? But, okay, fine. It's probably easier to conceptualize if we understand that the curl of F, either way we write it like this or like this, is the circulation density per unit area. So we're saying if we add up the circulation density per unit area over the whole area, that's going to be equal to the net circulation along the boundary. Okay? You guys are both staring at me like I'm speaking in ancient Egyptian language.
How's this different from what we're just doing? Or like from Green's theorem?
It's not. This is actually equivalent to the Green's theorem for circulation, but in space. In fact, this Stokes theorem is actually, if you think about if the curve were in the plane and the surface that we were talking about is that surface, that is Green's theorem. Okay? What Stokes theorem is just Green's theorem moved out into space. It's exactly the same thing. Because this is a circulation density. We're talking about the circulation density over a surface area, right? That's equal to the net circulation along the boundary. Now the boundary isn't just the curve, it's the curve in space, not the curve in the plane. And the whole area is this surface that could be any surface that's bounded by that path. I mean, it could look like this. That surface could look like this. In fact, that would have been a better picture. Okay? It could be this whole surface. Okay? That whole egg surface. That whole egg surface is bounded by that. Okay? So you'll use Stokes' theorem one of two ways. You'll use Stokes' theorem, or we will use Stokes' theorem. One way is to compute a line integral for circulation, but where the path is in space. They'll say, okay, here's f, here's the path, what's f dot dr? And rather than computing f dot dr, we'll do this. Now, in all honesty, that's not necessarily super easy to do because you're talking about computing a line integral and then turning it into a flux integral. And Kate, since you did your homework last week, you know that this is a difficult integral to compute, f dot n ds.
It's easy. That's why I can do it.
So you thought they were easy?
Yeah. It's just a lot of work.
It's a lot of work, yeah. Yeah, I guess it's a lot of work. I guess that's a fair thing, right? Or we might use Green's theorem, or I mean Stokes' theorem, or the same thing, to compute one of these and say that it's equal to this. Okay? Like we might say, okay, here's this situation. What is this equal to? Oh, that's the net circulation. All right. Do you want to do an example, I guess? Something with this might look like. Well, it's really just making sure we understand what the theorem says, and then we just got to use it. Like, so let's say, here's a field.
Okay, what's the ceremony thing for the 12th? What is it? Senior award ceremony? The senior award. Yeah. Okay, like they announce scholarships. I don't know if I have time for taking yeah. I'm sure you got it. And I think they like say okay. Would the direction just make it positive or negative?
Yeah.
So it has to be counterclockwise.
That's how we're defining it. Yeah. Okay, so we've got this field here, right? And so I'm going to say find that. Find f dot dr. Now, theoretically, we could do this problem. We could have done this problem as soon as we started learning about line integrals. As soon as we learned how to do line integrals of a vector field, we could have done this problem. We also could have done this problem when we learned Green's theorem. Sort of. The only difference now, though, with Green's theorem is the field actually has 3 dimensions. With Green's theorem, the field only had 2 dimensions. Okay? But we could have done this with just calculating f dot dr. Parameterize the surface, or parameterize the, I'm sorry, not the surface, parameterize the curve, and do f dot dr. Okay? We could have done that. But Stokes' theorem allows us to do this. Because we'll say, well, all right, well, f dot dr is going to equal to this surface integral of del cross f dot n ds, or d sigma. Okay? So now we need to think of a surface that we can use. Okay. Well, what's a good surface to use? In this case, the surface that we could use is just going to be that surface there. We can just do the surface that's in the plane, the surface that's bounded by the path itself. Okay? So we'll use the circle enclosed by x squared plus y squared equals 9 as our surface. All right, so let's do del cross f. What's del cross f going to equal? No, del cross f. So del cross f is going to equal, now, Kate taught me a way to write these as column vectors. And you guys did cross product races the other day.
I didn't know about that.
Huh?
I didn't know about that. I left it up on the board. Oh.
Okay, so show me again, Kate, how you do this. You cover up the first one, the top row, and so that's going to be the partial y of z squared, which is 0, minus the partial z of 3x, which is 0. Okay?
And how are we getting the partial?
This is, I'm just taking, I mean, this is a command, right? So you take the partial of. Then what do? I cover up the middle one? And I start at the bottom? So then what do?
So it would be partial z times 2y.
Of 2y, which is 0.
Minus the top with partial x, negative z squared.
Which is 0. So that's 0. Wow, this is stupid. Okay.
And then you cover up the bottom.
So then it's partial x of 3x, which is 3, minus partial y of 2y is what? 2. So 3 minus 2, 1.
You think that's easier than your y?
I think it would be once I get, if I got used to it, yes. Okay, so now this is what we have to do. We're going to compute.
Wait, what?
Huh? Is that not what you got for del cross f? Maybe I should just double check it.
It could be me though. Oh wait. Yeah, it's me. It's me. It's me. It's me.
You sure?
No.
Yes. Yes. Yeah, that's it.
You wrote negative 2z, but it's negative z squared. So 0, 0, 1.
Yeah.
How would you do I?
What?
What would it be for?
I is the partial y of z squared minus the partial z of 3x, which is 0. Both of those are 0.
Oh. Never mind.
So now we're going to compute this. This is like our new vector field that we're going to compute this flux integral of. And I'm going to even write it like this just because it looks. Okay. So how do we get ND sigma?
Oh, do we know how to do that?
Yeah, you did it last week.
Oh. Yeah. RU plus RV.
Correct. Now, time out though. With this particular surface, okay, n hat, okay, because I'm choosing this surface that's in the xy plane as the surface, the normal to that surface is just perpendicular to the xy plane. So for this particular surface, n hat is 0, 0, 1. Okay, now that, time out though, that's independent of the fact that that was 0, 0, 1. That's coincidence. Okay. Had we used another surface, okay, that, maybe it was that, then n hat would be, something perpendicular to that surface, then we would have had to use the parameterization of that surface. But now we don't have to. Okay? Because this particular n hat is very simple. So now we have this f dot dr is going to equal this. So we're dotting 0, 0, 1 with 0, 0, 1 d sigma, right? Which is basically going to be 1 d sigma. So what is that answer? Well, sort of, yeah. What is d sigma? It's a piece of surface area, right? We're adding up all 1 times the piece of surface area over the whole surface. What's that going to equal? Just the total area of the surface. Which in this case is just going to be pi times 3 squared. Because our surface is just that regular old guy. Or 9 pi. So this particular problem that we use Stokes' theorem on, we chose the surface, and we chose a surface that was very convenient and very easy, okay? Because figuring out that n hat was so easy. We didn't have to parameterize the surface even. Like, we had to do virtually no work whatsoever. Okay, sometimes though, we'll have Stokes problems where they give you the surface. Right? Does that make sense?
So what if it is like a surface like the egg? How would you know where the normal vector is coming from? You know where it is.
Then you have to have the parameterization of that surface, and then n ds or n d sigma equals
Right,
the cross product in n du dd. Right? Now, the other way that you could use, so in this particular way that we did Stokes' theorem, we were asking you to calculate this, and we did this. I could ask you to calculate this and do that. Does that make sense? The difference? I could say, find the flux of the curl of F, because that's really what this is. Right? And if you can really think of this is the flux of the curl of F. So what is this? The net circulation of F. So apparently, the net flux of the curl is equal to the net circulation. Does that make sense? Well, yeah. Now, conceptualizing that in your head, like visual, hard. I need a new mask. This one's super ugly. Kind of gross, isn't it?
Love it.
Good one from Snyder. You have homework. This is in 16.7. I'm only giving you a couple problems. 1, 3, 5, 13, 15.